Analytical Chemistry 1, Lesson 58. We conclude our class with looking at how titrations are carried out using redox reactions. Up to this point, we have measured voltages to determine unknown concentrations of species in cells. Now we take a rather different approach and set up a cell to monitor the evolution of potential during the course of a titration. As always, we start with a solution of some analyte species that is redox active, and we also have a titrant, which is also a reactive species. One of them clearly needs to be a reductant, it needs to be able to be oxidized, and the other must be an oxidant because it needs to be able to be reduced. If both analyte and reductant were in their fully reduced or fully oxidized forms, no reaction would occur and no titration could be performed. Also, their cell potentials have to be of a magnitude that, when combined, they produce a large enough positive cell potential so that their reaction will go to completion throughout the titration. Once we have the necessary reactants, we set up an electrochemical cell. On one side, we use some stable reference electrode. On the other is the cell in which we will perform the titration. So let's follow this using an example. The iron 2 plus 3 plus redox couple will be our analyte system. We will choose to analyze for iron 2 plus. We will titrate it so as to convert it to iron 3 plus in oxidation. We will use the cerium 3 plus 4 plus system for our titrant. Our burette will be loaded with a standardized solution of cerium 4 plus. It will oxidize iron 2 plus to iron 3 plus, and in the process it will be reduced to cerium 3 plus. Here are the relevant reaction equations. And let's use the silver-silver chloride reference cell. Connect it to the negative terminal, the black terminal of the voltmeter. We will use a platinum wire as the inert electrode in our titration cell. Recall that the silver-silver chloride reference cell has a standard cell potential of plus 0.222 volts. But we will use the saturated KCl variety, which has a potential of plus 0.197 volts. Commercial reference electrodes, such as silver-silver chloride or the saturated calomel electrode, have a built-in salt bridge and can be directly inserted into the titration cell. The probes are a complete cell and salt bridge. So here's what we have. A reaction vessel which we will fill with our analyte solution of iron 2 plus. A burette with our titrant, a solution of cerium 4 plus. A voltmeter with which we will monitor the solution potential as a function of the volume of added titrant. We will connect the silver-silver chloride reference cell to the negative terminal and immerse it in the analyte solution. To the positive terminal, we will connect a platinum wire that will be the electrode with which we probe the solution's potential. Let's use the following parameters for the condition of the titration we will follow. The iron 2 plus solution has a concentration of 0.01 molar. The titrant is 0.015 molar cerium 4 plus. The analyte's initial volume is 30 milliliters. Because these are both one electron processes, we can readily see that the equivalence point will be when the moles of added titrant equals the moles of original analyte present. Accounting for the difference in concentration, we find that the equivalence point titrant volume will be 20 milliliters. So what does the voltmeter read? Well, at the beginning, the reading is unreliable. If there was absolutely no iron 3 plus in the solution, the potential would be infinite. And that does not happen because there is a slight amount present due to reaction with atmospheric oxygen or perhaps impurities in the solution. In any case, the starting potential is uncertain and unstable and is not meaningful. It depends upon the local environment and the history of the sample and cell. It is not something we record. But once the titration begins, the voltage stabilizes and provides a stable signal. It is worth noting that we need to be stirring the solution to make sure the reaction achieves equilibrium. The reference cell has a finite time to respond to changes as ions must diffuse across the membrane and equilibrate with ions inside the electrode. So how do we determine the potential that will be measured at the platinum indicator electrode? Well, once we've added even the smallest amount of titrant, we now have measurable quantities of both iron 2 plus and iron 3 plus in the solution. The Nernst equation can be used to determine the half cell potential. And then, knowing the reference cell potential, we can determine the overall cell potential measured by the voltmeter. But notice something else. Not only is there both oxidation states of iron present, we have also been putting cerium into the solution, and both of those states are now present too. They also participate in the electrochemical processes at the indicator electrode. How do we compare these two reactions? The principle to appreciate is that there is only one potential at the electrode. Whatever it is, both the iron reaction and the cerium reaction must react and agree with that they produce the same value. If not, they will react with each other until they do agree. So here are both versions of the Nernst equation. The concentrations are all different. The standard cell potential is different. Yet the concentrations must vary in such a way that the half cell potential, E+, must be the same for both reactions. So how do we calculate the expected cell potential? Well, let's look at what happens. Now here's a legend for the species involved. We start with a large amount of iron 2+ in the titration beaker. We add the first small portion of the cerium 4+ titrant. It immediately reacts with a stoichiometric amount of iron 2+, and in so doing produces an equivalent amount of cerium 3+ and of iron 3+. We can see some iron 2+, iron 3+, cerium 3+, but what about the cerium 4+? Well, it is there, but at an extremely tiny concentration. We just don't know how much without solving a complex equilibrium problem. We know we could do it, but since both reactions must produce the same potential, and since we know the amount of both iron species, we can solve the problem with just that calculation. We know how much cerium 4+ we added. We read that off the burette. And that tells us how much iron 2+ has decreased and the iron 3+ has increased. Nernst equation, easy solution. So calculate the potential when we've added 1 milliliter of titrant. The original amount of iron 2+ is 3 times 10 to the minus 4 moles. The amount of added cerium 4+ is 1.5 times 10 to the minus 5 moles. After reaction, the amount of remaining iron 2+ is 2.85 times 10 to the minus 4 moles. The amount of iron 3+ now formed as a result of the reaction is 1.5 times 10 to the minus 5 moles, the same as the cerium 4+. And that must also be the amount of cerium 3+ that's formed as a result of the reaction. The amount of cerium 4+ remaining, well, we don't know. We just know it is very small. So use the iron Nernst equation. The potential is 0.691 volts. Now we could use this value in the cerium equation to find the cerium 4+ concentration. When we do, we find it's around 2 times 10 to the minus 22 molar. It is there, but not much of it. But its concentration is just right so that the cerium couple produces the same potential as the iron couple of that half cell. But remember, this is not what is measured on the voltmeter. We have to account for the reference electrode. We actually read a cell voltage of 0.494 volts. Let's do that again. What is the potential when we add 2 milliliters? Well, here are the calculations again. Substitute into the Nernst equation, subtract the reference voltage, the voltmeter reads 0.513 volts. Again for 5 milliliters of added titrant. Substitute into Nernst, subtract the reference potential, the voltmeter reads 0.542 volts. Now we earlier calculated the equivalence point volume to be 20 milliliters. What happens when we have added 10 milliliters, the half-equivalence point volume? Well, here are the numbers again, substituted into the Nernst equation. Note, however, that the concentration of both oxidation states of iron are the same. The ratio is 1. The logarithm of 1 is 0. The half-cell potential is equal to the standard reduction potential of the half-cell. And this is akin to the observation in acid-base titrations that pH is equal to the pKa at the half-equivalence point. Measured voltage is now 0.570 volts. Here's another calculation. It is for an added titrant volume of 18 milliliters, just a couple of mils away from the equivalence point. The measured voltage is 0.626 volts. Put it all together with the calculations at every milliliter of added titrant. And this is the titration curve in the region before the equivalence point. It looks just like all the other titration curves, doesn't it? Remember that at the half-equivalence point, the half-cell potential is equal to the standard cell potential of the analyte. But be careful, when the reference cell is not the SHE, then the measured voltage is not this value. You have to account for the reference cell potential. We read 0.575 volts at the half-equivalence point on the graph. Add back in the reference cell potential, and we get of 0.197 volts, and we get 0.767 volts, the standard cell potential of the iron 2+, iron 3+ redox couple. Now, I'm going to skip over the obvious next step, which is to do the equivalence point. Instead, I want to do the calculation in the region beyond the equivalence point. The calculation of the equivalence point is very different than what we've seen for Well, beyond the equivalence point is much like what we've just done. So let's look at that first. From the beginning, as the titration proceeds, the amount of iron 2 plus, the analyte, decreases while its redox partner, iron 3 plus, increases. At the same time, all of the added cerium 4 plus continually reacts almost completely and is converted to cerium 3 plus. The cerium 3 plus grows just as much as the iron 3 plus grows. Finally, at the equivalence point, all of the iron 2 plus disappears. The iron 3 plus and cerium 3 plus no longer increase anymore. However, as cerium 4 plus titrant continues to be added, the cerium 4 plus concentration now starts to increase. So look at what happened. We know the concentration of iron 3 plus and cerium 3 plus. That just comes from the moles of iron 2 plus present originally. And now we know the amount of cerium 4 plus that is in excess of the equivalence point. But we no longer know the iron 2 plus concentration, so we can no longer use that Nernst equation. But since its potential is still exactly the same as that of the cerium redox couple, we now use the cerium just like we used the iron. The differences now are that the amount of cerium 3 plus is constant, and the amount of cerium 4 plus just comes from the total amount added minus the amount that is now cerium 3 plus. So here are the calculations at 0.5 milliliters beyond the equivalence point. Moles of iron 3 plus and cerium 3 plus are equal to each other, and they are equal to the original amount of iron 2 plus that was present. Now a reminder, we have not solved the complete equilibrium problem when making these statements. We are counting, quite correctly, on the iron 2 plus that remains to be very small. It is, and the approximation is good, but remember that we have made approximations to get to these rather straightforward conclusions. We don't know the iron 2 plus concentration, we just know it is very small. The cerium 4 plus concentration now grows with the amount of titrant added in excess of the equivalence point. Take the total titrant volume and subtract the equivalence point volume to find the amount added in excess. Now use the cerium Nernst equation to find the potential at that positive electrode, the platinum wire. Use the correct standard cell potential and recall that we are using the numbers as if it is the reduction reaction. The reduced species is a product of a reduction reaction, so put the reduced species cerium 3 plus in the numerator of the reaction quotient and the oxidized species cerium 4 plus in the denominator. The calculation reveals the half cell potential to be 1.605 volts, and the full cell potential is 1.408 volts. Take a look at this calculation again for 21 milliliters of added titrant. Note how this time the reduced species amount does not change. No more cerium 3 plus is being made, but the amount of cerium 4 plus is increasing due to the added titrant. So really all we have to calculate each time is just the excess cerium 4 plus. The half cell potential is 1.623 volts, and the cell potential is 1.426 volts. Remember that it is the full cell potential that we are actually able to measure. Here is another calculation. We have added 22 milliliters of titrant, which is 2 milliliters added in excess. Substitute, and we find that the half cell potential is 1.641 volts, and the total measured cell potential is 1.444 volts. And we continue to add titrant and get this curve. So this looks very much like a very good titration curve. We can easily guess that the equivalence point is 20 milliliters. Something you may have missed, however, occurs at 2 times the equivalence point, or 40 milliliters on this graph. This is where the excess cerium 4 plus now equals the cerium 3 plus. So the log term goes to 0. Half cell potential is the standard cell potential of the cerium redox couple. Note how the analytical standard potential occurs at half the equivalence point, and the titrant standard potential occurs at twice the equivalence point. Don't forget to account for the reference electrode potential. 0.570 volts is the measured potential at the half equivalence point. Add in the 0.197 volts, the potential of the silver-silver chloride reference electrode, and you get 0.767 volts, the standard cell potential for the iron 2, iron 3 plus redox couple. Similarly, 1.530 volts is the measured potential at twice the equivalence point. Add in 0.197 volts, and you get 0.170 volts, the standard cell potential for the cerium 3 plus 4 plus couple. So the only thing remaining is to know how to deal with the equivalence point. The main problem here is that both iron 2 plus and cerium 4 plus concentrations are not known without some serious equilibrium calculations. We may not know the values, but we do know some relations. Imagine that the reaction had gone to completion and the iron 3 plus and cerium 3 for iron 3 plus equals cerium 3 plus. Now allow it to relax to equilibrium. A very small amount of cerium will surrender electrons to some equally very small amount of iron. The key is that it must be the same amount. Iron 3 plus decreases by exactly the same amount as cerium 3 plus decreases. And at the same time, the amount of iron 2 plus is produced must exactly equal the amount of cerium 4 plus that is produced. These two equalities must hold at the equivalence point. So look at both Nernst equations. We still cannot solve either one, but the secret is that we can solve them together. Add the two equations together. Note how the arguments combine inside the logarithm term. But note the above equalities. Things cancel. The log of 1 is 0. The half-cell potential is just the average of the two standard reduction potentials, and the measured cell potential is 1.037 volts. And there's the equivalence point on the graph. Before the equivalence point, the half-cell potential varies slightly around the standard reduction potential of the analyte. After the equivalence point, the potential varies slightly around the standard reduction potential of the titrant. At the equivalence, the half-cell potential is the average of the two standard reduction potentials. Now you can do these calculations in this manner for many redox titrations, but if the stoichiometry is not one-to-one, you have to be careful. Think it through and work in moles, and you can get this to go. The calculation at the equivalence point is just slightly more complex. So what if we were titrating tin 2 plus with chromium 3 plus? Here are the reaction equations, and here are the relevant Nernst equations. In calculations before the equivalence point, use the tin equation since tin 2 plus is the analyte. Beyond the equivalence point, use the chromium equation. But what about at the equivalence point? Conceptually, all the tin is present as tin 4 plus, while all the chromium is present as chromium 2 plus. But because of the stoichiometry, there must be twice as much chromium as there is tin. When it relaxes to equilibrium, two chromium 2 plus ions will surrender electrons to form one tin 2 plus ion along with the two chromium 3 plus ions. In the end, there are two relationships which must hold. We can substitute them. In order to add the two equations, we must also multiply the tin equation by 2 to get the denominators the same, and then substitute these equalities here into the chromium equation. Now add them and note how the reaction quotient Q cancels to 1. The log of 1 is 0. That term disappears. We solve for the half-cell potential, which is minus 0.047 volts. And depending upon which reference electrode is being used, we subtract it to find the measured cell voltage here at this equivalence point. Electrochemical titrations are very useful. There are many further complications, however, and if the stoichiometry is not one-to-one, or if one of the reactants is not aqueous species, but rather a solid, such as with a reactive electrode, or a gas, as with a standard hydrogen electrode, well, there's just a lot more to study. But I think you have got an excellent introduction to what is possible. Your future careers will certainly at some point need some kind of electrochemical analysis, and you are now off to a good start to understanding and working with such chemical systems.